Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future, binge watching for the exam. So today I'm going to finish the part on document stores. So I will show you how we can make it super fast. And then I will move over to query languages. We saw SQL for querying structured data. And so I will show you how it looks like when the data is messy. Before we start, I'm going to ask you a question just to make sure that you've been following. So which of the following is not one of the three constructs of Spark that manipulates RDDs? Is it trackers, transformations, actions, or creations? One of the four is not one of the three. So one is incorrect. Let's see what you said. And there is a majority for trackers, this one, and indeed, that is the correct answer. So we can create RDDs, which means that you read it from a file or you upload a Python list to the cloud, and then you have an RDD. That's the first thing you have to do. Then you have the transformations that turn RDDs into RDDs and other RDDs into RDDs. There's plenty of them, but it's lazy, meaning that if you just transform, nothing's actually going to be computed. But it's when you trigger an action that the whole thing starts executing. And an action allows you to either download the results to a local Python list or to show them on your screen in your Jupyter notebook, or if it's a lot of data, to write it back to HDFS or S3 in parallel. So creation, transformation, action. Trackers are a word that you saw in MapReduce. That is the name of a job tracker, task tracker. That's the name of the processes for the first version of MapReduce. So this is where it came from. Okay. So I'm now coming back to the part on document stores, which we are now going to finish. And I'm directly moving over to where we left, which is right here, indices. So first, I have good news for you. You've already seen indices. Who was in information systems for engineers? Who was not? So it will be new to you. So have you ever seen in a book, when you had a book on specialized literature in particular, or a textbook, and you go at the end of the book, and then you will find a few pages with an alphabetical list of keywords that you can look up, and it gives you the pages on which these words appear. Who has ever seen that? That is an index. Thank you, goodbye. The lecture is over. Now I'm going to show you how it's actually done in databases, because in databases, we do exactly that. We build these alphabetical lists of values, not words, which allows us to finally to find them very quickly. So I'm going to introduce that to you in the context of document stores, but in fact, they also work on relational databases. So it's just that they were adapted to documents. So imagine that you have a collection in a document store. It's a collection of documents, a collection of JSON objects, and you have billions of them, billions. The objects are rather small. You remember at most 16 megabytes per object, but there's billions of them, maybe even tens of billions, hundreds of billions, a lot of them. And you want to execute queries on these document stores. So on a relational database system, that would be with SQL. In the case of a document store, we saw the JavaScript API. And you saw that with the find function, you can look up documents that match specific properties, right? Now, what do you match? That could be a very, very precise filter, or not a so precise filter. For example, if you have billions of people and you look for one specific person, assuming that the name is actually very precise. For example, here it's a database of mathematicians. There's only one Euler. So if you say find name Euler, you will agree that will return one document, just one. This is what we call a point query, because it's a query that doesn't return so many results. 1, 2, 3 results, very, very small in comparison to the entire collection that might be petabytes of data. So this is called a point query. Now here I simplified by taking a name. You know, in real life, persons might have the same name, so you can think of it as the social security number or AHFAO, for example. Imagine the database of Seraph, which collects they have the database of everybody in Switzerland to collect the TV and radio fee. So that is a point query. Now there's also a query that might be a bit less filtering, like all mathematicians in a database of scientists. That's no longer a point query, because here you might have a few thousand documents returned out of billions. That still exists. It's just that the predicate now is a bit more generic and is going to return a lot of people, right? As opposed to point queries. Then you have range queries. Range queries do not filter for a specific value, but they filter for an interval of values. That means, for example, that you might want to find all the scientists between a specific year and another year. So here I took all of them greater than or equal to 1900, all of the 20th and 21st century. Could be a range. I could also have a conjunction of between this year and that year. That is called a range query. So it works with values that are numbers, that are dates, strings also, if you consider the alphabetical order of the strings. That is called a range query, right? And the goal of indices is to make these queries, the point queries and the range queries, super fast. In order for you to understand what I mean with super fast, is that if you did it in Spark, let's say, you have a data lake, you have 1 trillion documents, and you want to find a document with a specific name. Do you agree you're going to use the filter transformation, right? You create the RDD out of the data set, you dot filter and the predicate, and then you collect, right? So dot filter, dot collect. Do you agree with that? Right? But do you see it's going to take a while? Because now Spark has to actually read the entire collection over the cluster and launch all the executors and so on. So that's not going to happen instantly. It might be quick because it's just a selection, but maybe it might even take a few minutes if you're looking at petabytes of data, right? Or 1 minute, let's say. So it's not the sort of things that return instantly. Now, what if I told you that we can do that in 2 milliseconds? 2 milliseconds. And you get the documents. This is the sort of things that document source can do, and this is because of indices. And the way that an index works is exactly like at the end of the book, that you basically have all of these possible values, so the ones you have in your alphabetical list at the end of the book. So here I did it with colors. And the colors point to all the objects that correspond to them. So for example, yellow points to banana and ananas, orange to orange, green to kiwi and apple and so on, right? That would be akin, so the pointers would be like the page numbers that you find in the index, right? The page numbers would basically be the pointers to the pages. So this is what indices do. And the idea is that these values in the index, they are sorted. So here I did it more or less by wavelength, even though you could argue that brown actually is not on the rainbow, but sort of, right? So this is all sorted in a specific order, which makes looking up a value kind of quick. And then you follow the pointer. So this is the secret behind indices. So for example, if you're looking for orange, since the values are sorted, you just look it up and then follow the pointer and find the object. Now, let's take an example with the actual indices, because that was just a high-level example. Imagine that I have this collection, in that case, only 6, right? But you have to imagine billions of them in practice, 6 of them. And I would like to index the century. You see 20, 2019, -4, -6, 20. I would like to be able to quickly find the people corresponding to specific centuries. The first kind of index that allows you to do that is called a hash index. Who has ever heard of hash functions, hash indices, anybody? Some of you, right? So this is going to help. It's something that is found also in cryptography, in cryptocurrencies also. All right. So I can, in MongoDB, ask it to create the index. I don't have to worry about the details of that. I will show you the details, of course, but in MongoDB, you just need to say that, create an index, century hash, and then you wait for a while until it has built the index, and then the index is built. And now I'm going to show you what actually happens behind the scenes, what MongoDB is doing. So MongoDB is going to set up some, let's call it a 2-column table, but you can also think of that as an array, right? Or vector in Java, it's also called. Where we are going to have position 0, position 1, position 2, position 3, position 4, position 6, and so on, right? And so the array structures in programming languages, they are very quick. When you say, I want the element at position 5, it's instant, right? So we have that kind of structure. Remember that in some programming languages, the low-level ones, we start counting at 0, right? So this is why we say that 0, 1, 2. In the higher-level languages, we start counting at 1, but that's only a convention. So here we start at 0. 0, 1, 2, that's the position. So now what's going to happen is that I take that value for the first document. I'm going to go through all documents, but I start with the first one, and I see 20. I'm going to pass this value 20 to something called the hash function. The hash function, you can see as some kind of black box where you feed it with some value, and it spits out a position in the array. Right? So here I have 0, 1, 2, 3, 4, 5. I have 6 positions between 0 and 5. So H just gives you a value between 0 and 5, depending on your input. Think of it of a mixer, like you put the 20 in a mixer, you press the button, and it just outputs the sum position. And hash functions have very specific property. One way of putting it is that it's a bit unpredictable. You don't really know what number is going to come out of it, and yet it is deterministic, meaning that if I put 20 in it and 0 comes out, then I can guarantee you 0 will always come out of 20, always. That's deterministic. And the fact that it's unpredictable and very hard to invert, meaning that if I tell you the opposite, I want 0, what is the value that gives me 0? That's a very hard problem. Right? And that's how the blockchain works with Bitcoin, is that you actually have to solve this problem to find the value that gives you specific hashes. But anyway, I have this function h that is a given. If you want to know what's inside, it's just a bunch of addition, multiplication, and modulo calculation, really. It's plain simple. But the modulo and so on are picked in a way that it's unpredictable. So h of 20 gives me 0. Fine. So I put 20 at position 0, and I add a pointer to the documents. And now, rinse and repeat. 20, again. 19 gives me 4. I had no way to predict that. Just comes out as 4. So I put it in position 4 with a pointer. Then -4 gives me 3. Again, I had no way of predicting that. Just comes out of h, right? Then I have -6 that h gives me 1, and I have 20 right here. And now I'm done. I have built the index for the collection. And what you have on the left is an index. That is an index structure. And again, imagine if I have to build it for billions of documents, that's going to take a while. So it's not uncommon when you actually say create index in MongoDB that you have to wait for a couple of hours if the collection is very big, right? So for a couple of hours, it's going to build the index. But the thing is, after it is done building the index, your queries are going to be super fast. How? Look at this. This is a query now, after the index is built. The user arrives and says, okay, this is the query I want to execute in MongoDB. How can I use the index to execute that query? If I didn't have the index, I would have no other choice than to scan through the collection. But now I have the index. Can anybody tell me what I do with this query to use the index and find the documents? All you have is the function h. That you can take for granted. I give you the function h. It's part of the index too. Anybody? Yes, maybe the microphone if... yeah. So that there's a lot of people on Zoom, so that they hear you. Over there.
You will hash it and then check in the values in the table, and then you have a limited amount to look through, so it would be way faster.
Yep, absolutely, exactly. And how much time do you think it's going to take? So now I'm appealing to complexity theory, right? So complexity theory in computer science is a way of saying how efficient algorithms are. The kind of complexities you might have is that it could be instant, meaning that no matter how long the collection is, how large the collection is, it's always returning in a constant amount of time. Could be linear, meaning that as the collection grows, the time it takes also grows, but then could be logarithmic, could be exponential. Exponential is really bad. So what do you think is the complexity of that? How fast is it going to work? Who thinks it's linear? Okay, so nobody. And indeed, linear would be if you don't have an index. If you don't have an index, it's linear because you have to scan through the whole collection, right? So if the collection doubles, then the time it takes doubles too. So yes, it's not linear. That's the whole point of the index. Who thinks it's logarithmic? Who thinks it's instant? And it is in fact instant. That is the magic of hash tables. Look why it's instant. H is just a bunch of plus, multiply, and modulos, right? That's really something very quick. Just plus, multiply, modulo, instant, whatever value you give. Doesn't depend on the size of the collection, just a mathematical formula. Looking up in an array, this is in the working memory of the computer. And you know that working memory in a computer is called RAM, random access memory. And random access means you can instantly go anywhere in the memory of the computer. So going here, once you have the 4, is also instant. Following the pointer, again, because of random access, is also instant. Maybe it's on the disk, but then again, you just locate it on the disk and read it, right? So everything is instant. It does not depend on the size of the collection. I can multiply the size of the collection by 10. It might take more time to build the index, but once the index is built, constant time, a few milliseconds, right, in MongoDB. So it's really impressive because you can actually do the experience, the test in MongoDB. You click return, you press on return after that query, instant. You immediately see the document on your screen, even with a huge collection. So it's really amazing. So this is what hash indices do. They are in relational database systems like PostgreSQL, and they are also in MongoDB. But they have a problem. They do not support range queries. A hash index needs a specific value. You cannot tell a hash index everything between 10 and 15. A hash index cannot do that. A hash index needs equality, it needs specific value. Then the hash function is not perfect, right? So ideally, it would nicely put every number in its own cell. In real life, you're going to have collisions. You're going to have multiple values that are going to land at the same position. This is real life. So that's not such a bad thing, but it's going to slow down the system a little bit, right? And add on top of that, that if you want to avoid the collision, so if you want to have enough space that you don't have colliding values, two values in the same cell, then you need a very large array. So here I only put 6 cells in my index, but in real life that has to be very large. So hash indices are not the end of everything, right? And this is why we have something better than that solves this problem. That is called a tree, B plus tree index. And a B plus tree index, I'm going to briefly go over that, but give you a high-level intuition of them. It's very complex, by the way. Even for computer scientists, implementing a B plus tree index is very complex. So I just want to explain to you how it works on the very high level. So the idea, you remember this book with the alphabetic list of the words at the end? Well, this is kind of my alphabetical list of words. Look at how this is organized. So first, all of the words here, they are here at what we call the leaves of the tree, right? At the bottom. Do you see it's alphabetical here? C, F, H, I, L, M, P, S, T. It's all alphabetically sorted, right? That's the first thing. So this is like at the end of my book. Now what you have here just facilitates the lookup. Because if you look for something, let's say I look for merely. So I compare it, is merely before or after possess? It's before, right? M comes before P. It's like when you look a word in the dictionary, look for a word. So you go on the left, then is merely before come or before is, or here it is. So now you go down and find it. So this structure is a way to very quickly find a word. It's not going to be instant. So it's not like the hash table that instantly give you H and the position. What do you think the complexity is for locating a word? Who thinks linear? Linear means you would have to scan the entire collection. But here you don't, right? Because you go through the comparisons. Who thinks it's instant? Well, it's not, because I told you it's not instant. Who thinks it's logarithmic? And it is indeed logarithmic. And the way you see it's logarithmic is that if you have, let's say, a collection with 1,000 different values, 1,000 different values, and let's say you have 5 levels here, and now you double the size of the collection from 1,000 to 2,000, what it's doing here is only adding 1 layer, because you multiply it by 2, so it just adds 1 layer on the tree. And so this is why it's logarithmic, right? So you add a 0 to the size of the collection, and that adds 1 layer, 1 more comparison, right? Okay, so this is the idea. Now, there's a few, and here I really don't want to bother you too much with that, so just high level, but it's no big deal if the details are not all clear. The idea is that this is called a tree in computer science, and it's a tree, but not with 2 children. That would be called a binary tree, where you only have a child on the left and a child on the right. Here you see that there's even 4 children, right? So Comi's Merli, for example, has 4 children. It has 4 little arrows that go down. This is because of the way the disks work. Because when you locate a word, for example, in here, and you have to look at this block of words right here, what's going to happen is that you are going to read this from disk, this whole information with the words and the pointers. And you remember, I told you, I think in HDFS, that when we read from the disk, we don't read just a few bits. We try to read 4,000 bits at the same time, right? Yes?
So sorry to interrupt. So one or maybe 2 questions from the Zoom.
Mm-hmm.
So the first question is, does the lookup time of the hash index not depend on the choice of the value used for value used for hashing? And taking the example of the century, if many rows have the value 20th century, then they will also have the same hash value, meaning we might still have to look through the petabytes of data.
Yep. All right. So let me go to that. Then I'll come back and explain why the reading the disk in block actually is the reason why we do that here. So let me come back. So the first thing you ask, like, is the time to compute H, does it depend on the value? The answer is no, because it's just a bunch of mathematical operations. You give a number, you do a bunch of multiplication, addition, modulo, that doesn't depend on the number, the time it takes, right? It's just always the same mathematical arithmetics that you do, and this is the reason it's just in constant time. Does that answer the first question?
Yeah, so
I can give you an example of what this could be. H of x could be, for example, 15 times x plus 13 modulo 137 is an example of some hash function you could have, right? Okay. And the second question now?
Yeah, the second question is, so actually is, could you explain again how you put value in the tree?
Yes, I will. I meant the second question of the first one, because there was still another question in the first one that you asked that I need to answer. There was two components to the question, the former one.
Oh, so you
right?
mean a second component?
Exactly, I answered half of it. So I answered the half that says that the computing H is instant. Now there was another question on the fact that here there's multiple documents that have 20, the 20th century. Now there's still only 120, right? There's still only one value 20. But what happens is that you have multiple pointers here, right? You have a pointer to each document that has the value 20. Now, that's okay, but you just need to be aware that that's the difference between a point query, which would have very few pointers, and a not so highly filtering query that might have more. Now, of course, if you have a criteria, like for example, if you have billions of people, there's only been maybe 120 centuries in the history, in modern history, in humanity, right? So of course, if you have millions of people, a lot of people are going to be in the same centuries. Then you would not call that a point query, right? It would be a query that looks up people, but it's not highly filtering. And so in that case, it is true that you will need some time to go through the pointers, but you need to see that that doesn't depend on the size of the collection. That only depends on the number of documents for each value, right? So this is why we say it's constant.
Yeah.
But of course, it works best with point queries when you have something like the social security number, a primary key that strongly identifies the documents. Then there's going to be only one pointer in that case.
Yeah.
And so the second question?
Yeah, so the student says thank you. So the first question is
Yep.
answered. So the second is just, could you explain again how you put the value in the tree?
Yes, absolutely. In fact, I have animations for that.
Yeah.
I just have not gotten to it, but I will answer that. I will show you how to put the values in the tree. I have plenty of animations for that. I was only on a high level for trees right now. So this one I put on hold, and I will answer in just a few minutes. So let's come back to the tree. So I told you, when you read from the disk, you don't want to read just a few bits. You want to read ideally 4,000 bits. These are called the blocks, and that has to do with the mechanical head, the fact that there's mechanical parts that turn and so on in these good old hard drives. And so that's the reason why here we try to put several words together. On my slides, it's only 3, but in reality, that might be dozens of them in the same block, so a lot of them, with the goal that this is a disk block, right? When you read disk, this is roughly 4 kilobytes. So this is the idea that disks love block access. So that's the justification for putting several words together in here. Now, my tree has a few properties. For example, that's the root of the tree, right? And then you have the first level, and then you have the second level. Now, the nodes here that don't have any children, there are no more children here, right? There's no arrows that go out of this, so these are called the leaves, right? The leaves of the tree don't have any children. They are all at the same depth, right? So this is depth 0, depth 1, depth 2, and all of my leaves are at depth 2, right? Could be another depth, could be 3, could be 4, but it needs to be the same. Now, I have a rule that says that the number of children that a node in the tree can have must be in a specific interval. For example, it must be between 3 and 5. That you can configure. There's parameters to control that. But it's between 3 and 5. So you can have 3 children, 4 children, 5 children. Okay? There is only one exception, it's the root. The root is allowed to have less, but only the root. So that's why here the root has 2, that's less than 3, but that's okay because it's the root. Everywhere else, between 3 and 5 children. That is my rule. More generally, you can parameterize, right? It could be between 3 and 5, between 4 and 7, between 5 and 9, but roughly simple to double. Okay, so all my actual values that I want to index are at the leaves of the tree. Now, there is a little thing to think of, and that you might have seen in high school. Imagine that you are in the street and you see a bunch of trees planted along the street. There's n of them. How many intervals in between are there? Do you agree that if there's 7 trees, there's 6 intervals? If there's 2 trees, there's 1 interval, so it's n minus 1. What that means right here, you can see it right here, is that if I have 4 children, 1, 2, 3, 4, for this one, 4 children means 4 minus 1 intervals. So I have only 3 values in there. Do you see that? So that means that if I have between 3 and 5 children, then I have between 2 and 4 values in here. Everybody agrees? Right? So this is good to know because that means that these 2 and 4, between 2 and 4 also applies to the leaves. I have between 2 and 4 values on every leaf. Right? Okay, very good. Here I'm just repeating what I said, that for example, if you have between 3 and 5 children, that means you have between 2 and 4 values or keys or whatever you call these little things that you put in the cells. Between 3 and 5 children, between 2 and 4 values. But I have an animation, and here now I'm slowly answering the question that was asked earlier, because an animation makes it clear, and you see that programming this is complex, so I'm not even asking you to do that. So now I'm going to insert values in my tree. Just for the purpose of animating, I'm going to insert integers in growing order, but of course, in reality, that doesn't have to be in increasing order. It could be a random order, but just for the sake of animating. So I insert 1, I insert 2, I insert 3. At that point, I only have 1 node in the tree. It's not even deep, there's just this one, right? So there's not even any children or anything. Now I insert 4, and now I'm breaking my rule that I said I need between 2 and 4 values, between 3 and 5 children. So now I'm breaking my rule. What do? I split it. There you go. Now the rule is fixed. I again have between 2 and 4 values. I have 3 on the left and 2 on the right, so now I'm fine again. And the root has only 1 value, but again, that's the root, so it's allowed to have less. Everybody's following? Right. So now I'm inserting 6, 7, 8. Now I'm breaking the rule again. I'm only allowed to have between 2 and 4 values, right? So I'm splitting. Let's split right here, and that's what I get when I split, right? I just have now 3 children of the root. Now I add 9, 10, 11. Oh, now I'm breaking the rule again, so I'm going to split this one like this. You still agree? Yes?
So one quick question. So why the root is 4?
Why?
Why the root value is 4?
Why the root? Oh, why is it less? Or
yeah, I think he might consume why not the 3 or 2 or something else in the root of 4. I'm
not sure. Let me. Just first making sure that I understand the question.
Oh, so.
Oh, why the root is 4? Yes. Okay, so I will say why it's not 5. Okay, so let me explain that. Okay, going to go here. Yes. So there's a choice how you split, right? Actually, there's more than one way to split. I split between 3 and 4, but I could also split between 2 and 3, right? So I have 2 choices. Now, why 4? That's because the idea of the value that I put in here is that everything on the left is strictly smaller than this, and everything on the right is greater than or equal to this. And because of that, it's a natural thing to put 4 in there. I could have put 3.5, I could have put 3.6, you know, that would also have worked, right? But the simplest is to just put the lowest value from the right. That's why it's 4, right? Does it answer your question?
Yeah, thank you.
And that's when I look it up, I know that if it's lower than 4, I look on the left. If it's greater than 4, I look on the right. That's the idea of my index, right? All right. And that cannot be 5, because if I put 5, then it's no longer true that everything on the right would be greater than the value. Oh, by the way, maybe I should still tell you that. There's even more way to split, more ways. Look, I split it like this. I could also have split it like this, but I could also have done this, right? Or I could also have done this, and maybe this is what you meant in your question. So this is true. I could also have split it like this with 1, 2, 3, 4 on the left, 5 on the root, and 5 on the right. That also works, right? But it's just that in reality, splitting in the middle is a better idea, right? Because if you split it like this, then this is already full on the left. So you want to split it in the middle, just for being smooth in the growth of the tree. Yeah. Any other question after this one?
No
Yeah?
question.
Awesome. Very good. So we continue to grow. Then at that point, I just add, when I split, I just add a second value in my roots, 9, 10, 11. I add it again here. Now I fast forward, so now I add it all the way to 16. Now I have the maximum number of children in the root, right? Now if I add 17, I break my rule again. So I split it, let's say between 15 and 16. But do you see what's happening now? I propagated breaking the rule. Now it's the root that is breaking the rule, right? Now the root has too many children. It has 6 children. That's too much. What do? We split the root, and now we have an even taller tree. Now we have one more level in the tree. And this is how your B+ tree is going to grow and grow and grow and grow, and you just keep adding new levels as you split the nodes when they become too large, right? And concretely, when you do it on a real document, imagine you want to index this. So now you say create index century 1 instead of hash, you say 1. That's going to create a tree. 1 just means increasing, right? It's part of this API thing that it's just a convention of the API that A means ascending, in ascending order of century. So now instead of a hash table, I'm going to build a tree. So 20, I put it in there. That's a tree with just 20. 21, by the way, I moved Marianne Mezakani to the 21st century. She's in both 20th and 21st, but I just thought I'd change the value here. All right, so now I add 19 for Srinivasa Ramanujan. I told you, by the way, these rules between 3 and 5 children, between 2 and 4 values, it's a parameter, right? Here, I'm using a different value just because it's so small, and I wanted to show you an example of split. So now I'm assuming that even 3 values is too much, right? So just for the purpose of that slide. So I'm splitting. Then Euclid, -4. Here I can split, but I can also rearrange, right? I can just, oh no, I split it. Okay, so I split. Pythagoras -6. Here I can rearrange. So instead of splitting, I just moved over the 19 to the second cell. I can do that, right? Do you agree it's the same? I just move it over here, and that way I still have 2 values. Turing 20. Do you agree I have an index now? But now my index, instead of the hash, it's using the tree. How do I use the index? Can anybody tell me? Now it's a range query. Do you see it's a range query? I'm looking for everything greater than 19. Can anybody tell me how I'm going to use my tree index, my B+ tree index, to answer that query in logarithmic time? Anybody? Yes, we can bring the microphone over there. The people on Zoom need to hear you.
We probably will have to navigate all the branches on the right of 19.
Mm-hmm. Absolutely. So you take 19 and you start at the root right here. And then you see where 19 is. Is it before? Is it in the middle? Is it on the right? Turns out it's a match, right? But it could have been also in the middle. So now you know, because everything on the left is strictly smaller than 19, so we forget about it. Then we just have 19. And then once we have located 19, we just take everything that is on the right of 19, right? So including all the right part of the tree. And we follow all the pointers of all these leaves, this one, this one, this one, and this one. So I'm returning this document, this document, this document, and this document. Who agrees? Right? Who understands how it works? Very good. So again, building a B+ tree can be very complex. So you just need to understand the general idea that you keep adding values, the tree grows. And then when you look up a value in the tree, it's very efficient. It's in logarithmic time. You just start at the top of the tree, compare with the values that you see, and then you decide, do I go to the left? Do I go to the middle? Do I go to the right? Then you go down the tree, and at every time you decide if you go to the left, the middle, or the right, until you reach the leaf and you have found the value. Right? That's what you said by navigating, right? Awesome. Very good. So now, the good news is that if you are a user of MongoDB, you don't need to program any of that. You don't need to worry about programming how to build a hash index or programming how to build a B+tree, because that's a feature of MongoDB. All you need to do is ask it to create the index, and it will do it for you. You automatically have an index on some ID fields that is in every object in MongoDB. It's called _ID. You always get an index for free. That it does in any case. And for the other fields, you need to ask for them. If you don't ask, then you don't have any index. So you need to ask. And so the idea is that, let me show you concretely. If you have this index right here that you create, so you say DB scientist create index name.last hash, and then you wait for a couple of hours or a couple of minutes, depending on the size of your collection. And then you say, find name last Einstein. That's going to take 2 milliseconds. That's the idea, because we have the index. And all it took was this create index command over there. That's all it took to get the index. Now, here's another example where I create an index on profession as a hash. So I can look up very quickly exact values. And now I have a query that not only filters for profession, but also for theories. Profession alone might return multiple results. Maybe theories is going to be more precise. Who sees that here, the index will help to pre-filter the documents? Right? So we first use the index to get the documents that match the profession physicist with the index. And for theories, we just do it manually. When I say we, I mean MongoDB. So MongoDB uses the index to get the documents with profession physicist, and then scans through these results and looks for those that have theories relativity. The part to get profession physicist is instant, O of 1, instant. And theories relativity, it's a scan, so it's linear, but only linear in the sub-results of profession physicists. Who understands this? Right? So I have this slide right here. If you have no index at all, you have to scan through the entire collection, linear time, because you don't have any index. You need to look at the documents one by one. If you have an index, then what you do is that you use your index to pre-filter the documents and get few results, right? And after you have the results, you can scan them in memory. So in my example, profession physicist, you use the index to instantly get the physicists. And then for theories relativity, you have to do them one by one because here it was not indexed. That's the idea. Okay. Another example of B+tree. Now it's not a hash index, it's a B+tree index. Now we index the scientist by birth date and then by death date, right? So it's a lexicographic order. That means first by birth, and when they have the same birth, then you sort them by death, right? That gives you an order of the scientist. You can build a tree. And now if somebody says, find somebody born in 1887 and dead in 1946, that will be in logarithmic time, because that's a tree. In logarithmic time, you will find this document. For whom is that clear? Right? So you see, tree index with 1, 1, so that's ascending, ascending, and hash index, just saying hash, and then observe how these queries become suddenly so much faster with the index. So we are going to take a break because I see its line. I'm almost done actually with the indices. I just have a few examples to show, and that's pretty much it. I'm just going to finish with a few examples. So see you after the break in 15 minutes. and I'll continue from there. Thank you.